Okay, here we are, energy and momentum packet. This is problem number 5, the cannon on a cliff. So back in the very back, we got this problem. Here's a prompt. Cannon on cliff says we have a cannonball of mass m is loaded into a cannon of mass 250 m. Usually the guns are shooting things that are much smaller than them. That's what that is. Let's see, the cannon is at rest atop a horizontal cliff at height h, and the cannonball is launched from it horizontally with an initial velocity of v naught. Neglect friction. Friction sucks. Record answers in terms of given quantities and universal constants. So your answers have to have what's given. What's given? Let's see, m and v, v naught, and maybe g. All right. So let's see. Whoop. On number 1, on the dots below, draw and label all forces, not components, acting on the cannonball. The thing about the AP test is, like, in class we do free body diagrams and we do the dotted lines showing the components. They really, really don't like you drawing the components on their free body diagrams because there are 88,000 tests to grade and they just don't want to worry about it. Okay, they're there for 1 week, they're miserable, they're not getting paid all that much, and they're grading tests for like 10 hours a day. It's awesome. I mean, oh yeah, it's great as an AP teacher. That's exactly what you want to do during the summer. Let's see. On the dots below, draw and label all forces. So during the launch inside the cannon, we're doing the ball. So of course, we still have gravity. So there's gravity. And if we're inside the cannon, then we better have an upwards force. So this would be Fg or mg or force of the weight or whatever. Going up, you got normal force due to that cannonball being inside of the cannon itself, and as it's fired during launch, you can probably bet that there are high pressure gases behind it, pushing it forward with some very large force F, and we'll call it Fp, just for the force of the push, or to be ironic, it's the force of this momentum that is gaining. The force that's giving it this momentum, this impulse. So there you go. After the launch, it's in the air, and we're neglecting friction. So what force would be on it while it's in the air? Hopefully you know to only draw this one. This would be the force of gravity. Okay, that still exists on it, but that's it. If there is no air friction. Yeah, that's it. So moving on. Derive an expression for the final resultant velocity Vf of the cannonball just before it strikes the ground. So just before it strikes the ground, it would have had gravity working on it for a distance of h. It comes out of the cannonball with some velocity, and you can kind of bet that the resultant velocity would be off in some direction, like down to the right, something like that. But let's not use kinematics. I figure you can probably use kinematics, but let's not. Let's think about what kind of energy it has as it leaves this cannon. So as the ball leaves this cannon, it's got kinetic energy, right? And it also has the potential to get more kinetic energy on the way down. And so to do an energy equation, we're going to say that the energy, well, let's see, the mechanical energy anyway, energy in the first place, should be equal to the energy in the last, right before it strikes the ground. No outside forces here, no friction. So in the beginning, what kind of mechanical energy do we have? We have the mechanical energy due to gravity. We have mgh. Am I using all the right things? Yep, cannonball is just m. And h is the height of the cliff, plus the kinetic energy that has 1/2 m v, and that's v naught squared. Okay, and this equals all the energy at the end. Well, the energy at the end, right before it strikes the ground, is going to be kinetic energy. So all the potential has been used up, turned into kinetic. And so that's equal to 1/2 m the mass Vf squared. And so that's our setup of the equation. And what we want is we want to find that final velocity. So let me just move some things around. Let's multiply everything by 2, get rid of the halves. So if we multiply everything by 2, we have 2mgh plus mv naught squared is equal to mvf squared. And look, everything has m. Let's get rid of m. So we have 2gh plus v naught squared is equal to vf squared, and that's odd because that's one of the kinematic equations, right? Vf squared is equal to v naught squared plus 2a change in position. So there you go. Last step. 2gh plus v naught squared is equal to vf, and that's what we want. And I think that should be, yeah, that's it. So move on to the other page. And let me go to the top there. It says, number 3, derive an expression for the range x of the cannonball from the launch point to where it strikes the ground. So we're looking at change of position, and it's in the horizontal, and there's no acceleration in the horizontal, so whatever velocity that we had coming out of the gun, if we go for some period of time, we should get that range. Now, do we know the time that it takes to get to the ground? And so using kinematics, yeah, we kind of do. Because in the y direction, we have initial velocity of 0, it shoots horizontally, and we have gravity, we have the acceleration due to gravity g. So what I'm going to do is I'm going to find out that time using our, well, what my class uses as the third equation. We've got the change in position y is equal to the initial velocity in the y direction times the change in time plus 1/2 a/t squared. But there is no initial velocity in the y. It shoots it off horizontally, so that's gone. Y is h, and that's equal to 1/2. A is g, and t squared is what we want, that t. Let's move some stuff around. 2h over g, square root them, and that's equal to our time. And that's what we're going to put in right there. Well, right there. So the horizontal change in position is equal to v naught times the change in time, 2h over g, and that's it. There you go. Moving on, derive an expression for the velocity v prime of the cannon immediately after launching the cannonball. So what's going on there? What's the velocity of the cannon before launching the cannonball? It's still, right? So this is an explosion, or in other words, an inelastic collision that's backwards. So let's think about that. We can use momentum. Momentum in the beginning should be equal to the momentum in the end. What's the momentum in the beginning before the cannonball shoots, or before the cannon shoots the cannonball? Likewise, Newton's third law. Before the cannonball shoots the cannon, it's 0, which means in the end it must be 0. So if the initial momentum is 0, the final momentum must be 0, but we know things are moving after it fires the cannonball. And so what you're looking at is the equation, let's see, mv, m of the cannon, times v of the cannon after the collision, plus m of the cannonball times v of the cannonball after this collision. And we know that the mass of the cannon is 250 m, and v of the cannon is what we want. The mass of the cannonball is just m, the v of the ball is v naught. And so to rearrange this, I can say mv naught negative is equal to 250 mv of the cannon, and we want that. And both sides have m, that goes away. Divide by 250, v naught over 250 is equal to v prime of the cannon. And so the velocity of the cannon is only 1/250th of the velocity of the cannonball. And that should make sense, because if it didn't work out like it did in this equation, who knows what would happen. You might blow the cannon back at the same velocity as a cannonball, but in order for that to happen, they'd have to have the same mass. So if you ever go and shoot a gun, or if you ever go out and shoot guns, that's why you don't blow your arm off. You might bruise it, but the recoil velocity isn't as high as the velocity of the shot. Let's see. On the graphs below, sketch the kinetic and potential energy of the cannonball as a function of time. Again, this is a sketch, so don't worry about putting numbers on here. Just draw a rough sketch of it. Kinetic energy by time. This would be a lot easier if it was kinetic energy by distance. Because if we look at our, if you look at this, as we go down h, at this point we've lost half of our potential energy and it went to kinetic energy. At this point we've lost 3/4 of our potential energy, it's gone to kinetic energy. So that's a pretty straight line there as h changes. But we're not talking about h, we're talking about t. Had to screw it up like that. So let's think about what happens over time. As something falls over time, it gets faster and faster and faster and faster and faster at this exponential rate. And this is due to the equation. We have 1/2 at squared, and we have this like v, or well, it doesn't get faster and faster and faster at an exponential rate, but it goes farther and farther and farther. That's what I meant to say. It goes farther and farther and farther at an exponential rate. So a change in y is equal to 1/2 at squared if we start off from rest, if we just drop it. So 1 second later, it might go 5 meters. 2 seconds later, this is going to be 2 squared. 2 squared is 4. 4 divided by 2 is back to 2. 2 times 10 is going to be 20. So in the first second, we go 5 meters. In the second second, you've gone another 20. So, yeah, anyways, moving on. So we're looking at kinetic energy versus time. What is the equation for kinetic energy? It's 1/2 mv squared. How does v change over time? This is distance. How does v change over time? Well, final velocity is equal to initial velocity plus at, right? So as time goes on, 1 second later, if our acceleration is 10, after 1 second, our velocity should be 10. After 2 seconds, the velocity gets another 10 greater, so 20, then 30, then 40 after each consecutive second. But just like how distance was exponentially increasing because the time was squared in that equation, the kinetic energy would be exponentially increasing because velocity is squared in this equation. So every second that goes by, our velocity is getting 10 bigger because gravity is about 10, the acceleration due to gravity is about 10, but that increase is going to be huge right there. And so just as an example, if m was 1, here's our equation, 1/2 v squared, if m's 1, okay? After 1 second, our velocity is 10. And so 10 squared is going to be 100 divided by 2, that's going to give you 50. Okay, that's after 1 second. That's your kinetic energy just in the vertical, just considering a drop. After 2 seconds, your velocity is going to be 20. So we have 20 squared divided by 2. That's going to give you 200. Okay. After 3 seconds, your velocity is 30. And so 30 times 30, we have 900 divided by 2, 450. Okay, so this is an exponential change. And so with kinetic energy versus time, we need to go over here and we got to make sure that we have this curve that is going to be exponentially getting bigger and bigger and bigger as time goes on. What we also got to make sure is that this is all the kinetic energy. Not just, you can't say just vertical, just horizontal. This is all of it. Okay? Energy doesn't care about direction. So in the beginning, we start off with some v0 velocity. We start off with kinetic energy in the beginning. And as time goes on, we get more and more and more and more and more and more. Okay, exponentially increasing. It's probably even be even steeper than that, but we have no scale on time. Likewise, for potential energy, where does the kinetic energy come from? It comes from the potential energy. So in the beginning, we would start with some potential energy, and by the end, we would have none. So while kinetic energy is exponentially increasing, potential energy would be exponentially decreasing. And those would be your graphs, just sketching. Using clear, coherent sentences, describe the effects of increasing the mass of the cannonball and the changes that would result. So if you were to increase the mass of the cannonball, basically by that equation, momentum in the beginning is equal to momentum in the end. In the beginning, if your momentum is 0, again, here, m of the cannon, v of the cannon, plus m of the ball, v of the ball, and moving this around, mv of the cannon is equal to negative mbvb of the ball, or maybe we'll say the cannon goes backwards to the left. If we increase the mass of the cannonball, how does that change this velocity of the cannon? Well, if you increase the mass of the cannonball, the recoil velocity of the cannon starts to get higher and higher and higher. All right. If you were to, if you push something that is very, very small, if you push a child, because you're just mean like that. If you push a little kid, a little kid goes flying, you might move back just a little bit. You walk up to one of our offensive linemen and you push them, you might not push them too far. You might actually end up pushing yourself farther back than they would move if they're much more massive than you. So as you increase the masses and as they become more equally, more of the same mass, well, their velocities go shooting off, one to the right, one to the left, but those ratios start to change. With equal mass, they should move off with equal velocities. If you have a heavier one, that would move off slower, and the fast one would move off, or the small one would move off a lot faster. So, I'm just telling you a story right now, but you need to figure out on your own how to write it. Using clear, coherent sentences. If the mass of the cannonball was a lot bigger, or made a lot bigger, then it wouldn't move off as fast. All right, and plus the cannon would start to move off even faster than before. And so that would be the last problem, number 5, and we'll close up with that.